and officially start this first of the hopefully many soft robotics debates. So just to give a kind of quick introduction to the audience, my name is Laura Blumenschein. I am a new assistant professor of mechanical engineering at Purdue University, and I'll be moderating the debate today. I'd like to just start by thanking everyone who's shown up in the audience, and also thanking our participants here for the debate today, our panelists for agreeing to come into the open and have these discussions in front of more people so that we can start to get these ideas more traction in the community. And it's my hope and the hope of the debate organizers that by having debates like these out in the open, that we can start to kind of show the community at large some of the discussions we're having inside of our research groups, and also to spur new ideas generation so that we can start to push the field forward in new and interesting directions. So without further ado, I'd like to get into the topic of today's debate. So today our panelists will be discussing the merits of different approaches for controlling soft robots. Specifically, we'll be looking at and comparing the use of morphological computation and design methods to more traditional control methods and how these have been adapted for soft robots. So morphological computation methods focus on offloading the intelligence of the control from the quote unquote brain of the robot to the body of the robot, and leveraging the compliance within the soft system, where traditional control methods have used a lot of the inherent knowledge that has been developed for rigid robots, and seeing how we can start to take these and combine them with machine learning techniques and other techniques to leverage them for our new compliance systems that we've developed in soft robots. So as I kind of mentioned before the debate officially got started, we'll start with opening statements from all of our panelists here, and then we'll move on to an open discussion and question and answer section. Before any of that gets started, there'll be an opportunity for a poll to kind of get where you as the audience stand on this topic, whether you have a stance one way or the other, and we'll see how that shifts by the end of the debate today, or whether it does. And when we get into the question and answer section, you'll be able to submit your questions through the chat, and we'll hopefully have time to ask some of those for our panelists here as well. So before we get into the meat of the debate, I want to give a quick introduction to all of our panelists today. You can find their full bios on the Soft Robotics Debate webpage, where hopefully you found the link to come join us today. And I encourage you to go look at those because they have lots of amazing accomplishments and lots of amazing work in this field as a whole. But just to give a kind of an abbreviated introduction to save some time for the rest of the debate today. Acting on the side of the morphological computation, we have Dr. Thrishantha Nanayakkara and Dr. Helmut Hauser. Dr. Thrish is an associate professor of design engineering and robotics at Imperial College London, where he directs the Morph Lab. In his career, he has worked at leading laboratories for robotics and neuromotor control at institutions like Johns Hopkins, MIT, and Harvard. Dr. Helmut is an associate professor of robotics at the University of Bristol and the Bristol Robotics Group. He is interested in understanding and employing the underlying principles of how physical properties of biological systems facilitate learning and control. Meanwhile, on the other side of the debate, we have Dr. Cosimo Della Santina and Dr. Manolo Garabini. Dr. Cosimo is an assistant professor at the cognitive robotics, or in cognitive robotics at TU Delft. His main research interests include modeling for control and model-based control, combining machine learning with model-based strategies for soft robots, and the design of soft robotic hands. And Dr. Manolo is an assistant professor of robotics at University of Pisa. His main research interests are in design, planning, and control of soft and adaptive robots, from single joints to end effectors to complex multi-degree of freedom systems. Last but not least, we are joined by Dr. Barbara Mazzolai, who has her feet, I would say, squarely in both sides of this debate. She is the director of the Center of Microbiorobotics, and her current scientific activity focuses on bio-inspired soft robots, and the merging of the fields of biology and robotics to create new opportunities in both fields. And so with those introductions out of the way, I would like to ask for the opening remarks, starting with Cosimo.
Okay, thank you very much, Laura. Can you hear me?
Yep, we can hear you.
Okay. So let's start. The topic at hand today is morphological contribution versus traditional methods for control and planning in soft robotics. And I am listed as part of the Control team. And I will not argue today for the need of using a certain amount of high-level control in soft robotics, because this is, in my opinion, a necessary step to create intelligent systems, which does not really need arguing. I would like instead to focus on another question. Can morphological contribution be understood without traditional methods? And my answer here is no, it cannot. To convince you about this claim, allow me to address what I believe being a common misconception within soft robotics community by saying that control theory is not taking a microprocessor, writing some code, which reads some sensors and command actuators. So what is control theory? And I have here some holy books. And Strogatz defines dynamics as the subject that deals with change with systems that evolve in time, whether the system in question settles down to equilibrium, keeps repeating in cycles, or does something more complicated. It is dynamics that we use to analyze the behavior. And for what concerns control theory, we have the Sontag here saying that control theory is the area of applied oriented mathematics that deals with the basic principles underlying the analysis and design of control system. To control an object means to influence its behavior so as to achieve a desired goal. So control theory is therefore really the art of dealing with a system which evolves in times, as robots are, and acting within some design space so to make the system behave as we wish. There is no mention of microprocessor, sensors, actuator here, and these components merely serve as a possible implementation of the theory, and as such, they are often not even mentioned in control papers and text. But any kind of component that we can employ to produce the desired dynamic behavior is a controller, even the robot's mechanics itself. This may sound as an odd statement, but it's actually a quite uncontroversial one. So let's look back at the very dawn of control theory. Although controllers were known since the antiquity, the first theories of control were invented in the 17th century by the very Hooke of the Hooke theory of elasticity and by the Dutch astronomer Christian Herens. And they proposed to use centrifugal forces as feedback action to regulate speed and apply it to the construction of precise clocks by means of a modified pendulum. Hooke then used the mechanism to create a telescope that could rotate at constant speed, therefore following a star in the sky. In the 18th century, Watt proposed a system based on similar ideas, maintaining a constant steam pressure within its engine, and tanks of water were later added to physically realize integrators, and so on. So are these implementation control or are they morphological contribution? I would say that they are clearly both. In the same way, I don't see how the shaping of soft robots' compliant behavior should be something inferent. In the end, what is an elastic field if not a physically implemented algebraic loop? To conclude, I believe that control theory is the preferred language and the closest allies of physical intelligence rather than its fierce adversary. Even more, I think that ultimately understanding morphological intelligence requires, if not only, at least largely, understanding its relationship with control theory, making the use of classic methods in soft robots an unavoidable necessity. Thank you.
Great, thank you so much, Cosimo. And to kind of ping pong the debate back and forth, we'll move on to Helmut Hauser.
Can you hear me?
Yes.
Yes. Okay, brilliant. That was a really nice introduction, Cosimo. Actually, quite a lot of points I would agree on. Because I did my undergraduate actually in control theory, so I know about control theory as well. The question that we discussed today is, as I've written it down here, for reliable soft robotics should be focused on morphological computation. And for me, for this question, the answer is clearly a yes. There are many, many points why I believe that's true, but today I just, for the sake of brevity, I'm going to focus on 3 main points. So point number 1 is, I believe morphological computation is a necessary next step to take us outside of the box of assumptions that are currently holding us back in robotics. Now let me explain what I mean by that. For example, if we take soft robotics as a field and how it relates to the conventional field of robotics. Now, conventional robotics is quite old. It's highly successful. It has been proven to be incredibly useful. But it also comes with a set of very deeply ingrained assumptions that are not necessarily true anymore. One of these assumptions is that we need to build bodies for robots that can be easily modeled and therefore easily controlled. Unfortunately, a lot of times people forget the other side of the coin of this assumption. It also implies that the environment needs to be easily modeled and controlled as well. Now, while this is very easily realized in a factory floor, for example, it's almost infeasible when we bring robots into the wild or into our living spaces. Another implication is a constraint in how we think about robots should be constructed. So the design toolbox is then only rigid body parts and electric or hydraulic motors. And this very problem is or has been one of the biggest motivations for people to think about soft robotics, to step outside of this box of assumption and think about a richer set of design tools. And the result is a completely new set of solutions for previously unsolved problems in robotics. And I would argue that soft robotics, what soft robotics did for conventional robotics, morphological computation can do for other conventional approaches like control, computation, sensing. It questions the underlying assumptions. It questions, do we have to base control only on models or their approximations? Can we have computation outside of a Turing machine? Can it be analog, for example? Can sensors do more than just measuring? And morphological computation can provide, therefore, a new set of viewpoints and consequently also a new set of solutions. But point number 2 is morphological computation has been proven over and over again in nature. Evolution has produced numerous solutions for very tough engineering challenges, and very often morphological computation seems to be at the core of these solutions. Also, evolution was able to produce very intelligent biological systems and behaviors long before there was any brain or control involved there in a classical sense. I agree, there's still a lot to do. We have to understand this principle more formally, but it's clearly worthwhile to think about how biological systems are doing that, because they outperform robots in almost any task, especially in energy efficiency, robustness, adaptivity, autonomy. These are all properties that we're desperately seeking in modern robots. Point number 3 is morphological computation is not just about finding a clever way of control for a robot. It's much more. It's about, for example, also building intelligent sensors that can do much more. They can dynamic filtering signals out of a noisy environment. They can change their body morphology to be more robust, to quickly change the range of sensitivity. Morphological computation can provide frameworks for very small robots to build systems that are so small that actuation, sensing, and computation has to come together into a very small space. You cannot assemble these robots anymore. It has been shown to facilitate learning if you have a good body. It can help for human-robot interaction, and it might be even a missing link to build truly autonomous systems where we meet engineering and biology. So it has been demonstrated as being a very inspirational source for a lot of new solutions by stepping outside of this box of these assumptions that we have in these very well-established fields. So in summary, I've just these main 3 points, right? I think it's good for us to take this next step, and for me, it's the next logical step, right? People took this very big step from robotics to soft robotics, and the next one is for me also to go to morphological computation. But also, it helps us to understand the solutions that we can find in nature to make better robots. And I think in general, morphological computation, for me, it's a fundamental shift in the way we think about problems, the way we look about problems. Instead of squeezing them into an existing framework, we can build a new framework to understand it better. And I'm very excited to look forward to see what people are doing in the future with the inspiration of morphological computation. So with that, I hope you vote in favor of our statement. Thank you very much.
Great, thank you, Helmut. And again, to kind of ping pong back and forth. We'll go now to the other side of the debate. So Manolo, if you'd like to give your introduction and your response to that.
Okay, so thank you, Laura, for your invitation and all the stuff that actually set this debate up. Very interesting. I mean, first time that at least virtually part of something like that. Very interesting and exciting. So yeah, let me start with a very bit of history of let's say the world in which we are as roboticists. So the 20s, actually, the first, more or less, it was the first work with the word robotics. Okay, so it was like a machine, almost a slave, able to do works that people are not able or don't really want to do. Then after a while, let's say from the 50s to the 60s, first robots, the Unimate, I think someone of you had the chance to have a look at it. The Unimate started to work in factories. And at the times, the problem was that clear. So you have to move something from a place to the other in a very structured environment without any interaction. And the goal of the problem was definitely clear. So you have to maximize performance. That in such a scenario is minimizing cycle times, maximizing accuracy, and predictability of the motion of the robots. So the result, the solution, the answer to this problem being, and it is still, since the problem, in the cases in which the problem is still the same, the solution is a very accurate machine. That means rigid, bulky, heavy bodies. And if this is not enough, controllers that make them even stiffer. And that actually solves the problem. So still today, if the problem is just move a part, a well-known part in a well-known environment without any interaction, with cages that separates the robots from the human operators, this is still a very good solution that works perfectly fine. But since the 60s, actually, Ralph Mosher, a very smart researcher from at the time GE Labs, a very smart researcher that wanted to build the first exoskeleton. So Ralph Mosher realized, at the best of my knowledge, he was the first that realized that rigid robots were not the solution for a different problem. A problem in which you have still to move as fast as possible, because of course we want maximum performance, but in case the scenario is not that structured, in case you may have interactions with human operators, in case this interaction is so close that actually the human operator is wearing the body, the rigid robot. So in all these scenarios, actually, Ralph Mosher, since the early 60s, understand that rigid robots were not the right solution. And after him, a couple of decades after, actually, one of the first that realized that something different was to be designed was Neville Logan. So Neville Logan understand that some degree of compliance is really, really helpful when robots have to interact with an unstructured environment. When robots have to interact with other agents, for example, that can be autonomous, like other robots, or human operators, the behavior of which, of course, is less and less predictable with respect to autonomous machines. So in this case, compliance can be helpful. then after different ideas, different approaches to introduce compliance in robots. So the first one was the active approach. The active approach, so I'm referring to all the research line that can be, so to say, called under the large name of impedance control. This line is now, let's say, mature, and we can say today as products some of the collaborative robots that actually embed this principle, compliance and at large impedance control. And this is the so-called active approach to include compliance in robot bodies. On the other side, there is the so-called passive approach. So actually include elastic elements in the robot design, in the robot bodies. And so far, this approach has been pursued in different, of course, ways. One is the literature, the works that actually include this compliance in, let's say, this lump compliance in specific parts of the robot body, for example, at the joint level. So there is a lot of literature along this way. We can call it like articulated soft robotics. And this compliance at the joint level can be fixed. I'm referring to the series elastic literature from the end of the 80s with the famous seminal work by Pratt. And also this compliance can be varied at physical level. And finally, there is the approaching with the compliance is distributed along the robot limbs, and we can call that the continuum of robotics. So, how is today the level of this robot? Well, articulated soft robotics actually is a bit more mature, and we can now see robots that are building by startups and spin-off companies, and that are trying to going out from the research labs and reach the market. This is a very early stage, let's say, these are very early stage products, but at least in some, let's say, niche markets, they are now promising. Different stories for continuum soft robots. They are much more early stage, and partly they are really able to leave labs. And this, of course, one of the main reasons behind this is that when you add another component, and who among the audience and among the speaker is a mechanical engineer knows that very, very well, has this lesson very clear in his mind. Every time that you add another component, of course, its design and the design of the dynamics of the overall system is different and changes and has to change. And also this component can add a lot of novel failure mode, hardly thinkable at the beginning of the process. So imagine the difference of inserting lumped elasticity in a system and continuous elasticities. It means a lot of difference. We are speaking of including some components to, let's say, an infinite number of components, new components in the system. And this makes the design and, of course, the control problem much, much harder. And to conclude my statement, continuum soft robots have a huge potential. Of course, as Helmut said in the previous statement, we have a world of exemplar of this living robots, and I strongly think that I'm strongly convinced that a day we will have such a biodiversity, let's say, in robotics. But we need to solve the planning and control problem. And the difficulty of this problem is an order of magnitude higher with respect to the difficulty of planning and control problem of rigid bodies, of rigid robots, and of articulated soft robots. A couple, if you want, of examples of the challenges that we are facing in controlling continuous soft robots are the dynamics. The number of states of the dynamics is exponentially increasing with number of elastic elements that we add in the system, and the interaction of the states is also very complex. And this produces challenges in the way we model these robots. So, for example, there is, for the articulated soft robot, there is the SPONG model, and is well known and well agreed among the community that this model is there. And we, when approach the planning and control problem, go there and look at the Marx-Spong's model and have a clear reference. For the continuum soft robotics, this kind of model is not yet there. So we have the Ritz-Galerkin approximation, we have the Euler approximation, we have the bio model, we have the constant curvature model. But actually, we are not yet at the point in which say, okay, so this is the problem, this is the model, go there and plan and control the system with that model. And this, of course, this more complex dynamics pose challenges not only from the modeling point of view, but also from the planning point of view. If we think, for example, at the trajectory optimization approach, we will have to optimize the trajectory for a system, taking into account 2, 3, 4, n at the end elements, and at the end states of the robot. So the computational time and even the complexity of the problem is much, much harder. Finally, last but not least, the underactuation, the degree of underactuation of the problem is extremely high for an hyper-redundant structure as the one of the continuum soft robotics. So for that, novel control algorithm, of course, leveraging on the classical control theory that I think, so in this, I'm really sharing the point of view of Cosimo, because if not move from there, we will not have any guarantee in terms of stability, in terms of robustness, and so on and so forth. So finally, and to conclude, I think that we are really now at the point in which we have to focus on the planning and control challenges for having continuum soft robots that leave their labs and are ready to move in the real world.
Okay, thank you so much, Manolo. I think that that's a lot of good points that we need to think about for maybe for soft robotics in general. So to get the other side of the morphological computation point of view, we'll next hear from Dr. Thrish.
Great. Thanks, Cosimo and Manolo. Can you hear me?
Yes, we can hear you.
Great. Yeah, so there's somebody in the audience asked to explain what morphological computation is and then differentiate that with differential equations in robots. So I'll give a kind of a quick take on what I mean by morphological computation. So for me, the morphological computation is computing on one hand and then kinematics and dynamics on the other hand coming together, right? So computing, when I say computing, that means like it's a map from one domain to the same domain or to a different domain. For example, if it's a continuous signal, if you map it to a discrete signal, that is a mapping from time to time, but in one continuous domain to another discrete domain. Or it can be a time domain signal mapped to a frequency domain signal, or its frequency domain equivalent. So that is another domain. So that is computing. And then you have dynamics, from forces to accelerations. So when they come together, amazing things happen. For example, the cochlea of the ear, right? When pressure waves come and hit the eardrum, and then that propagates those vibrations to the cochlea, which is a tapered tube with liquid, and then because of the tapered nature of this tube, the frequency components get separated. So it is a real-time conversion from time domain signal to frequency domain signal in a tube. And then the cochlear hair picks up these frequency components from different locations and then feed the brain, the auditory cortex, with all these signals. So, so there's a cochlea where the dynamics and computing come together to do a Fourier series computing using just vibration dynamics of liquids, and then the neural computing happens. So one cool thing about this phenomenon is that it is very real time, it is very fast, and then that the neural computing cannot achieve with its slow communication fibers. So another example, if I take a mountain goat hoof, like if a mountain goat slips on those cliffs, there's no chance the brain can react, because by the time the brain knows, it will at least about 120 milliseconds. And then any thinking about 50 milliseconds and commands coming down to the muscles, another 120 milliseconds to 200 milliseconds, that is not enough to survive on a cliff. So we found in our recent work that the vibration dynamics in the hoof itself manages a vector transformation, like so the slip vibrations in tangential direction gets converted to some other directions that are really helpful to brake autonomously at the hoof level, just like a ABS system in a car, or how the ice skaters would brake on ice, right? So that kind of real-time behavior emerges from this kind of computing and dynamics when they come together. So there are three things that these things help. One is that the real-time nature of this phenomenon, and then the relevance. So for example, this helps to condition the dynamics so that the dynamics solve this problem for another form of control to take place, right? So it is like, for example, if a bicycle rider rides on a bumpy terrain, so the brain would get the knee joint to be kind of bent and then working like a shock absorber. And then that simplifies the bumpy world to the brain. Okay, so you don't worry about the bumpiness of the terrain. You focus on riding, and then the knee joint just takes care of kind of filtering, for example. But the same brain is doing both, like conditioning the knee joint and then riding. So just feeding the slow controllers with relevant information, and then local autonomy to take care of unnecessary information for that kind of slow controllers in the brain is one thing that happens, right? And then the other thing is the entropy reduction of all these signals going to controllers. So when the signals are noisy, so one thing you can do is like feed all the noisy signals to the controllers and all these observers, Kalman filters, things like that, and then expect them to solve the noise reduction problem. Or you can condition the body to reduce the entropy of the world, the uncertainty of the world, so that you can deal with the simplified version of the world and then deal with those dynamics, right? So for example, the foveated vision of the eye, for example, so when you look at something, you see some like the focal point sharp, and then other things a little bit smudged. And then this is done by the retina itself, the organization of the retina. And then when you feed a sharp point, a sharp image surrounded by a smudged image to the brain, the neural dynamics autonomously converge to process the sharp image faster, and then the other things get kind of filtered out. So the morphology of the retina is helping the neural dynamics to converge. So they kind of is an interplay between these two. So these three things, right? So real-time nature of computing, some things cannot be done with very slow controllers, relevance of signals, and the entropy of signals. So when we go to control, so when we look at biological species, so there are three things that happen in concurrency. So one is, as I said, like for the bicycle rider, for example, there is conditioning happening, like to control the stiffness and the impedance of the knee joint, and then at the same time there is movement control. So the outer loop of movement control is supported by the inner loop of conditioning the knee joint, and then there's an interplay, and then there's passive dynamics, right? So the passive dynamics allow like its own course to minimum intervention, right? So for example, like if you take an octopus, so when octopus wants to catch a prey, it just throws the limb, and it doesn't go to control everything, it just throws it, and then it knows how to throw it, and then the passive dynamics of unrolling a rope just takes, and if they miss the target, they don't do corrections, they just pull it back and throw again. But if it wants to, if it catches the prey, when it brings it, it conditions the limb to make basically two rigid links, and then one joint, and then pulls it back. So there's conditioning happening, and then when it is needed, it exploits passive dynamics, and then when needed, when it makes it rigidified, and then change the kinematics so that the control is different. So there's these three things, the interplay among these three things: conditioning, movement and force control, and passive dynamics. This interplay is really interesting. And the other in terms of organization of these controllers, it seems that most soft organisms like octopus, their controllers are hierarchical than central. So there's a lot of peripheral nervous system autonomy, and then there's like the whole feeding central bus going around the 8 limbs, and then there's a central control too, right? So I'm not denying that control is important, but the problem is that the conventional controllers we are using have challenges when it comes to contact, right? For example, with all the advanced control theories we have today, we cannot trust a robot to hold a hamster, right? So a live hamster, but we can hold a hamster, and then we can we can play with it, and the hamster will stay in the hand. But get a robot to hold the hamster, even a soft robot to hold the hamster, you cannot trust it. We don't know where the thing is missing. Like, so it is like you can have soft fingers, you can have model-based controllers, probabilistic controllers, stochastic controllers, all these things. You can throw anything, but we cannot trust these things. Why? Because there's something missing in the real-time nature of control when things are uncertain, and then the contact forces are very kind of stochastic. Right. So there is an opportunity for a control theory to improve to accommodate these things, to accommodate passive dynamics, to accommodate the conditioning, to accommodate controllers, like so all these things happening together, right? I can propose 3 or 4 things, 4 opportunities for control theory to improve to accommodate these phenomena we see in morphological computation. One is less separation between controller and the dynamic system. So we have some kind of a tendency to separate, oh, this is the hamster, and then the task is now to control the hand to hold the hamster. So that immediately sets this boundary between the hamster is the problem, and then I have to control it, and that messes up the whole thing. So rather than using the dynamics of the hamster as part of the computational process to solve the problem, right? So considering dynamics as part of the computation is an important thing to move forward. So Another thing is the move away from control action at fixed sampling intervals. So even in let's say control theories that accommodate morphology in the control, like variable structure control, for example, they should happen at a fixed sampling interval and then at rapid sampling, and then that causes jitter and all these problems, right? So, but if you want to use passive dynamics like the octopus, you don't have to sample at 200 hertz, like, so just let it go and then just check if when you are stretched, whether you caught the prey or not, right? So the octopus just uses that. So when intervention is needed, you sample, but when it is not needed, you just let it go. Right? So that has to be improved. And then the third thing is the concurrent nature of conditioning and control, like the bicycle rider example, has to be accommodated. So there's just not one layer of control. It is so many things happening in the same time, one supporting the other. Okay? So the movement control or the force control can happen. And then at the same time, you can have a parallel pathway to condition the dynamics. Like, for example, if I hold the hamster, I can have movement control of my finger, the posture control of my fingers. And at the same time, I can have stiffness control, conditioning my posture of the fingers or the stiffness of my fingers so that the hamster will feel relaxed, right? So that is the third one. And then the fourth is designing systems with real-time responses to uncertain things, and then relevance, focus on the relevant state space rather than a fixed state space. From time to time, the number of states that matter can change, right? And then the entropy in mind, right? So the entropy, let's say, for example, if I palpate a soft tissue to locate the location of a hard nodule, we take various actions like, stiffness control of the fingers, posture control of the fingers, percussion, tapping, and all this behavior control to reduce the entropy of the signal, right? So the uncertainty of it. Or let's take a simple example, like I'm given something to weigh, right? So my mobile phone, I would just not hold it, and then I may have time to time uncertainty of my perception of the weight of this mobile phone. But what I do is like bob it up and down slightly by controlling the stiffness of my elbow joint from time to time, and then that conditions my tendons to reduce the entropy of the uncertainty of my estimate of the weight. So, and for the goat hoof, for example, the passive dynamics of the goat hoof itself reduces the entropy of the world for the brain to deal with, so the goats can just relax in the cliffs. So these four things are really important. So finally, what I want to say is, at the end, we end up in enriching the control theory. There's no debate about that. So we come back to control theory, but the only thing is the way we approach control today has major limitations to deal with real-time contact control tasks like the hamster or the goat hoof. For example, I can pose that kind of benchmark tests for control theory that a lot of controllers, we call themselves to be very advanced control theories, can fail. So we have to see why they fail and then see what we can learn from this kind of natural systems that seem to be benefiting from multiple pathways of control at the same time, conditioning, movement and force control, and passive dynamics together, so that we can end up enriching control theory in the future. So I agree with Cosimo and Manolo. There's no argument that control is important for morphological computation. And then I agree with Helmut that we had to rethink about the framework of formulating these control problems accounting for the benefits of morphological computation. Thank you.
Great. Thank you, Thrish. And last but not least, I'd like to hear from Barbara about maybe a little bit of both sides of this, or whatever your unique perspective, I guess, on this kind of topic here.
Thank you, Laura, and thank you for the introduction and the organization. This very interesting chat and discussion. So the speakers already presented valid and clear motivation for pro and cons versus morphological computation in soft robotics. So probably I can just add another point, another view. That is, so the community is growing, we know, and we are developing different kind of soft robots that are designed for different kind of applications. And so this is an aspect that is related, of course, to the control strategies that we are identifying, we are selecting. For instance, if we are considering medical application that, in fact, many groups are addressing, the goal is to develop a compact manipulator in which we want to achieve a compliancy, variable stiffness maybe, but we need accuracy. And in that case, the manipulator is moving in quite a constrained environment that is given by our body, the surrounding environment. And so in this case, probably also more traditional approach or something derived from the traditional approach, like model-based approaches and so on, are very valid. But if the goal is to develop soft robots that have to move and act in a very unstructured environments, for instance, soft continuum manipulator to grasp unknown object in a blind condition, in dirty condition, if the robots has to deform, so they change the body, they grow, they self-heal, or they have to evolve. So in that case, we are in front of completely different problems. We are in front of non-uniform geometry, non-linearity in the case of soft robots that show these kind of abilities. At the same time, we need these kind of abilities to open new application scenario. So there is not, I think, not just one solution in terms of control, but it's strictly related to the application that we have in mind. And in this phase, probably also hybrid solutions are an option because we are moving in a terrain that is quite unknown from a control point of view, because as I said, we are opening completely new scenario in which the robots don't have anymore the same morphology, the same shape, they are deformed, they have to adapt. So these are high plasticity of this robot that can adapt in a very changing condition. And so the goal, the opportunity, I think, of the community is exactly to think in another way, to attribute a lot of importance to the body, because as also the speakers say, one of the approaches is to take inspiration or at least some ideas from biology. And if you look to biological system, all of them attribute part of the load in terms of computation to the body, to the morphology, to the peripheral nervous system. Trisha described the ability of octopus, but in fact these animals has most of the neurons in the arms, not in the brain. And probably because it is not able to control the complexity of the morphology, the complexity of the interaction, this multi-degree of freedom, infinite degree of freedom with the environment. And also, probably we can take this kind of inspiration. So, I mean, we can integrate when is needed, centralized control with distributed control, giving a lot of importance to the morphology, to the materials, to the interaction with the environment, because the environment plays an important role. And it can help us in reducing the complexity of the control. So, as you know, one of the models that we are investigating is a plant, and they are perfect in terms of morphological computation because they don't have a brain at all. But plants are able to interact with the environment, they perceive the environment, they take a decision, they don't have a brain, so they communicate, they interact with the other living organisms in the environment. So this means that they use a lot of computational load, they attribute a lot of computational load in the materials, in the structure. So the geometry is fundamental because we can really attribute a lot of importance to the geometry and the way in which the materials interact with the environment. Our goal, I think, is reduce the complexity as the natural organism has to do to survive, because in this way they reduce the energy that they need to act in a very complex environment and to show multitasking, because usually the robots are designed for just one task, but the multi-organism, the living organisms are multitask, so they need really to reduce the complexity because otherwise they die, because they spend a lot of energy. So energy, from my point of view, is another consideration, another important aspect that is strictly related to the solution that we implement in terms of control. They are no more separated. So we need to consider the design of our robot in an integrated view, in an integrated approach, and the solution that we implement in terms of control are strictly related. And in this sense, I very close to the morphological computation approach, but at the same time, I know that the traditional controllers can help in some situation, especially when software robots have to play in a more accuracy way, because they have to show more accuracy. And so application, again, is very important. And when we select the strategies in terms of control, we need to consider also why we are designing this kind of software robot. What is the scenario, what is the environment, what is the body, and then identifying different kind of solution for the control.
Fantastic. Thank you, Barbara, and thank you to all of our panelists for giving your opinions on this topic. So I would say, as expected, you guys had so much interesting stuff to say that we ran a little over the expected amount of time for the opening statements, but that's okay. So I'd like to reserve a few minutes at the end of our hour-and-a-half-ish to do some closing remarks and specifically kind of get your guys' opinion on where this field and this question should go in the future. But right now, I'd like to jump in to some questions, some of which you saw ahead of time, and hope to spur a little more discussion back and forth. So I will, I was going to try to post these to the, oh, maybe I won't be able to post these, but I'll start with some of the questions that I sent you guys ahead of time. So first, kind of targeted at the morphological computation side of the debate here. First question is that we kind of talked a little bit about this. The name morphological computation really promises that we'll be able to create designs that replace some or all of the control of the soft robot with the response of the body, if that's just in the structure of the body or in sensors that we distribute within the body. For now, however, a lot of the designs that we're creating that purport to be morphological computation amount to complex power transmissions or complex kind of passive dynamics. So how do we move these designs forward towards creating truly responsive intelligence within the form of the robot without just overloading the complexity of the system, as I think Cosimo and Manolo kind of pointed out is a potential way that this could be headed. So if Trish or Helmut want to talk on that.
Yeah, so when we when we design a system, let's say, for example, we have a 3-link manipulator, and then we derive the, let's say, dynamics, and let's say the Jacobian matrix, we need to map the forces to torques. So immediately the equations become complex, right? So if you work backwards from the equations to a 3-link manipulator, it looks simple, right? So that means, like, if we can start with the differential equations we want to solve, and then we can work backwards to a mechanism that can realize these very complex nonlinear differential equations. It can be our own observer, right? So of states, or it can solve a part of. So I think Helmut can say about it. Like, so there is a way of computing, for example, these ideas are that, right? So getting a soft robot or a physical system to solve differential equations, right? So it is not disagreeing with control, it is control, but implemented in a different way, right? So it makes it more real time. So you don't need solving differential equations in a computer, or expect something else, some algorithm to converge, because these things are very distributed and then real time, right? So that is how I view it. Like, so it start with a desired set of differential equations, nothing in dynamics, and work backwards, find a way to work backwards to a physical dynamic system to solve it.
I guess, Helmut, would you agree with that? Because it seemed like you were coming at your introduction came more from the point of view that this isn't just control. This is maybe something else.
Yeah. So I think this is also the misunderstanding that a lot of people have about morphological computation, right? Because it's very easy to give simple examples everyone understands, right? You have a mass spring temper system. It's basically, it controls its position, right? At its resting length. So this is basically a BD control implemented in a mechanical system. Now, this is exactly the same example that I guess Cosimo gave in the beginning with the steam governor, right? Where you, or was it a steam governor example, I think, where you have this kind of rotating mechanical device that then pulls up, basically pulls a line, and then it self-regulates it. So this is transferring the differential equations that you found to be the controller for your plant and translate that into a mechanical system. Now, when there were electronic circuits, people did that with electronic circuits because it's much faster and much better. Then you can program it in some couple of code of lines and so on. And it's very successful, right? But I think morphological computation goes far beyond that. And Trish gave a couple of examples of those, right? Where you suddenly get hierarchies, where you don't control every single degree of freedom. You assume that certain parts are outsourced to self-stabilization, right? In the tendons of our legs when we run, for example. It's not actively controlled by the brain. It's more this higher level control. Also, Trish mentioned that you don't have to control constantly, right? At every single sample time. A very good example I like a lot is the Cornell walker, which is based on passive walkers. And they don't constantly push it, but just around this limit cycle, they give it a little push just to keep it going, keep it going, keep it going. And this is very energy efficient, right? And there are a lot of these examples where I can look at the overall system, and also what Barbara mentioned, the interaction with the environment is very, very crucial in nature, right? Locomotion depends very much on the interaction with the environment. Swimming, flying, there's a lot of going on in the morphology, with the morphology of the environment. Usually in an engineering system, and so this is not just on the control, but engineering in general, we try to simplify it as much as possible. So you do exactly what you wanted to do. You want to build it like a machine that is doing one particular task. But biological systems have to do many tasks. And I think Barbara mentioned that it also, you have to do multitasking, so they have to optimize for different kind of things. And therefore, you have these much more complex morphological structures. So I think morphological computation is a general way to look differently at machines, how we build machines. And it's more bio-inspired in my opinion. It doesn't have to be, because you can come up with solutions which you can't find in nature. but just looking differently at the problem from a different angle, you see suddenly solutions that you weren't aware of that because you were thinking through one little kind of tube that you're looking at the problem.
Yeah, that's fantastic, and I think Cosimo obviously looks like he wants to jump in and say something, and I think a little bit to encourage that, I'd like to direct a little bit of something from what Cosimo said to poke at this question. So Cosimo, you mentioned using the language of control theory to describe morphological computation. I wonder how you would kind of explain that in regards to what Helmut just said in how you build morphological computation. What is really the difference you see there?
Yeah, I mean, I think that we are actually agreeing much more than expected in the end, because what I'm hearing from Trish and Helmut and also from Barbara actually is not really to not use traditional methods. It's actually just to not use microprocessors. And I agree. I don't like microprocessors as well. You say no, but to describe those properties, you use words like self-stabilization, limit cycles. These are control concepts. So this is control theory. I mean, at least this is what I mean for control theory. What if you take this book you see for control theory, not PID, not H infinity controllers.
Can I answer it? Yes. Yeah, so I use this vocabulary because I'm coming from control theory, right? That's I think about morphological combinations through differential equations, but that's not necessarily the case, right? I mean, when you talked in the beginning about control theory and the definitions, and I've read my Eduardo Sontag as well, and Mazzolai and my Khalil as well, and I mean, I agree. At the end, there's one way. If we formalize it, morphological computation, right? There are different aspects. It's not just control, there are different aspects. One way to do is through mathematical tools, right? And control theory is using mathematical tools. And I don't say we shouldn't use mathematics for control theory. What I argue is that if we just stick through this kind of assumptions that we have in control theory, we might overlook important things. So I think at the end, when we have more solutions, it might be canon in control theory, right? That's completely fine with me. I have nothing against control theory. I just think it holds us a little bit back, like the same way that building machines, the way we build, hold us a little bit back in what we could do in building more intelligent machines and more interesting machines, right? Soft robotics stepped out of this kind of box and came up with completely new ways to think about robots. And we also do that with chemistry, with hybrid systems, with minimatology, synthetic biology, and all these kind of things, right? So these kind of things help us to look at the problem from the outside. And that's what I'm suggesting, that morphological computation is a way to look at the problem from outside of the established kind of very old research fields, very successful ones like control theory.
Okay, and I think this is a great jumping off point to kind of the second prepared question that I have here, which is more targeted at the people coming from the traditional robotics control side, because I think what Helmut has said as kind of could be summed up as we need a new direction to approach this, otherwise we're going to get trapped in our assumptions. So what I'd like to hear Manolo and Cosimo speak on is, since traditional robotic control methods are developed with rigid robots in mind, when we use these control methods, we often use simplifying assumptions to create models, or have kind of other things we must give up about the actual dynamics or mechanics of the system, or otherwise we must choose design that better match when we do actually want to create those systems that we can take out into the world. I think Manolo mentioned well that that a lot of the compliant systems right now are these jointed series elastic actuation systems and not our continuum robot systems. But I think there are a lot of nonlinear dynamics of soft robots like buckling that have desirable behaviors. So what limits are we putting on our soft robotic systems by taking the approach of coming from traditional control methods, and how do we best adapt traditional control methods without limiting our designs and just making kind of bad rigid robots? Like, how do we step past just making rigid robots that don't work as well because now they're compliant? So, yes.
Yeah. So this is actually the point to be addressed by the recent control and planning theory for soft robots. And actually, maybe not everyone knows that compliance has been taken into account since the very beginning of control. Why? Because often they have to use the compliance in the model of the robots to model undesirable effects that the robot showed up when they moved too fast. And the control, in order to solve the, let's say, the first problem without any interaction, any human operators around, and so on and so forth. So control methods there were designed to specifically cancel this undesired compliance that at some point showed up, for example, oscillatory effect in the robot movement. So the point now is to actually change the problem and take into account that first, what we want from planning and control now is not to destroy the soft robot behavior that with a lot of effort we embedded in the robots now. And specific examples here is, for example, if you take into account classical theory of controlling an elastic system, you can profitably apply feedback linearization or dynamic cancellation in linear systems or backstepping control. And with this method, you can really reach position control and so on and so forth in the very same way as they did for a lot of time, for a lot of years with rigid robots. But what's the price? The price is to completely cancel the dynamics of the robot. So to say you will have this spring already there, you first cancel the spring and then put it back by control. So that's obviously not the way to act today with this soft robot. So for example, in this specific case, one thing that we realized very recently in our, let's say, endeavor to control and plan to do planning and control for soft robots is that in our approach, actually, a lot more important should be the feed-forward action, so the anticipatory action, if you want to look at it from the, let's say, motor control theory, instead of the feedback one. So you should rely more on the feedback provided by, let's say, on the stability provided by the system, and force the minimum feedback action. So if you want to simplistically see the minimum position and velocity gains, if you think of a controller as a classical proportional derivative controller action. So minimum magnitude of proportional and derivative controller, the minimum that you can add just to enforce stability in the region that is interesting for the specific task. And then you should rely on the feed-forward action to obtain performances.
So Manolo, not to kind of cut in here too much and interrupt your point, but I have a quick question off of this, which is, if we are relying on feed-forward actions, does that require that we need good models of these soft robotic systems? And that seems especially difficult given some of these more extreme out there materials and designs that are being developed.
Mm-hmm.
That's my. May I just
Sure, go ahead.
close it?
Yeah.
That is my, of course, concluding remark. In case we have a good model of the robot, we can profitably find an anticipatory reaction, a typical reduction, relying on optimal control and numerical trajectory optimization techniques. And in the other case, so if we don't have this model, if this model is not good enough, probably because the nonlinear torque deflection or torque velocity characteristic of the soft bodies, or because of our task involves contact, and we have all the phenomena that Trish mentioned in his sentences. In this case, we could profitably rely on iterative learning and learn the action, learn the feed-forward action. In both of the cases, it's likely to happen that we will not be able to derive this feed-forward action in real time. In the first case, probably since the dynamics of soft robot is very complex, it may happen that the optimization or the model-based derived feed-forward action needs some computational times. In the other case, it may happen that we need several iterations in order to derive the proper feed-forward action by learning. In both cases, we can profitably leverage on experience and through machine learning techniques build libraries and policies in order to have at some point a map that is able to provide us the correct feed-forward action just based on some task parameters. And then we don't have to compute any more, so to spend any more time in order to compute an optimal policy, or we don't have to spend any more iterations in order to learn feed-forward actions. Wonderful.
Trish, did you want to respond to that?
Yeah, I mean, in all cases, like it seems that, let's say, take the octopus, right? So the octopus has this central nervous system, and then partly residing in the brain, and then this central bus, and then this eight tentacles, and then they have their own local ganglion controllers, right? So the central controller doesn't necessarily have to know the full dynamics of the whole entire 8 tentacles, right? So it just can send like the desired signals, and then the local reflexes can work using passive dynamics. So that is like, for example, when it wants to catch a prey, it just throws the limb, and then when it was to fetch it, it conditions. Reduces the state space to 2 joints, basically, right? And then whenever it needs, it releases the full state space, and then it is needed to throw. So there's nothing called a fixed set of dynamics there, or fixed model there, right? So when you need, you release it, and then full hyper redundant system. But when you don't want it, like you just freeze it, and then two-link manipulator when you fetch it, right? And then things happening at different time scales, like our cortical control happens with the forward models and predictors to predict the consequences of the motor commands because the loop is too long, right? But there's a spinal cord that works in about 15 millisecond loops to make local corrections, and then the spinal cord doesn't really worry about models. It just gives like bam bang control, and if you prick your finger on something, just take it off, right? You don't need a model for that. And then you just give a big command, and then the passive dynamics of the hand takes care of it. So this kind of brings home the message that model-based control is not something we should look at as a fixed thing, as a fixed model all the time. We should be able to switch among different models and different modes of using the body, right? So that is one. And the other thing is, if a model works all the time, you don't have to keep it in a slow controller, right? Take an inverted pendulum, for example. If you try to balance the inverted pendulum, let's say the trunk of the body of a bipedal walker, and then you can stabilize that by pushing the cart back and forth. And then if the controller is successful most of the time, and then the joint can observe that, oh yeah, it is trying to numerically implement a spring here, right? So it is when you have a positive angle, it is going to push it, and the negative angle you push the other way, it is a spring. So why can't I grow a spring in this joint so that that controller can be drawn, right? So so it is not a fixed. Just because I have a model that works doesn't mean that that should be the final solution. It can be delegated, which can be more real time, less entropy, less energy control. It is control, but in a different way.
Yeah, and I think that's a great point. And Cosimo, I think this is kind of getting into some of the stuff that you said. So if you'd like to comment on that real quick.
Sure. I mean, just maybe also for the audience, just to try to put things in places. I think here with this question, we are talking, in my opinion, about two kind of application of control theory. There is the physical one, which is the one that Trish is talking about right now. And I mean, I understand that we are more and more agreeing on that part, so I'm not doing any other comment on these things. Regarding, I mean, at least for now, regarding the computationally implemented control, which maybe we can disagree a little more on this. I still believe that it's very important to have it. And again, for the audience, the way in which you typically do model-based control in soft robots, either a simple kinematic one or more complex dynamic one, is by discretizing the continuum structure. So you take the continuum structure, you discretize it in space, and not in time necessarily. So what you have is that you associate a configuration to each of the discretization, either use finite elements or constant curvature models or more sophisticated stuff. And then you have a finite dimensional model, and you develop your controllers using it. So going back to the initial question, yes, I believe that that this way of proceedings, which is kind of extending our vision of rigid robots to soft robots, because in this way you kind of identify locally continuum but well identified joints, is somehow constraining the way in which we look at the problem. And I like very much the comment that Helmut did before about using morphological computation to look out of the box. But I definitely think that in future control theory should look more and more at different problems, and therefore constraining less and less the structure of our systems.
Great. And I think in the interest of time, we'll, even though this is a very good discussion that I'd like to have continued maybe off debate, I'd like to move on to a question that I'd like to direct at Barbara, which is the kind of third question we have here, which is, question number 2, as I've labeled it. You mentioned a lot about different applications require different control strategies, and I'd like to ask, what should our kind of short and long-term goals for controlling soft robots be? Is this focus of different control for different applications, is that a long-term goal, or is there someday when most of our control, as I think Cosimo was kind of alluding to, will be morphological computation, or these fields will kind of meet in the middle in some way?
Yes, but I think that, of course, all the positions are fine, are good, because, I mean, are correct, and it's true. But probably we need also to consider that soft robots are designed to operate in a completely different environment with respect to the traditional robots. And so we need also to consider that probably they are less precise, and this is exactly what we want from this kind of robots, because they are designed for completely different application. Trisha mentioned again octopus. So when an octopus wants to reach an object in water, it's not precise at all, but it lands several times the arms in order to reach the object, and doesn't move the arm in this way because it's in water. And in this way, it increases the friction. And this is convenient from an energetic point of view, but this is not. So again, really depend by the scenario that we have in mind. Sometimes control everything is not the right approach because we don't have the model of this robot. So I agree with Manolo in also this approach of predict, anticipate also some action of the robot. From my point of view, is correct. Sometimes they cannot be model based because we don't have analytical model of this robot. So we need to maybe move to model free approaches that probably are more correct when we address, as I said, non-uniform geometry, and many of the robots that we are developing don't have a uniform geometry, and also they are not linear. So we need to take probably a different kind of approach. Also, we mentioned machine learning approach, hybrid system probably in the short, medium term. As I said, model-free approach could be fine, and probably in the future we need to put in this kind of model, this kind of control, the intrinsic properties of the material. Because this is part of the story. This is really complex, I know. I don't want to say, but this is probably in the long perspective. But this is exactly what we need now. So consider the materials, the property, the multi-functional materials in the loop. And now we are just consider structural materials, so materials like different kind of silicons, but it's quite simple, less complex with respect to the material that we see in nature. But we need this kind of intrinsic properties because if we are able to put in the loop the intrinsic material properties, we can again reduce the complexity of the control. Even if in the beginning is really difficult, because I think that one of the criticism is that bioinspiration is not really implemented, not yet. We really need a contamination from these different disciplines to think and to see the structure, the problem in a different way. So we need this contamination. I really believe in the interdisciplinary approach to solve this problem, because otherwise the risk is that we continue to see traditional or semi-traditional approach to solve a problem that are completely different. So software robots are designed to operate in different scenarios. They don't want to substitute the traditional robots. Traditional robots work very well. They are really efficient, accurate. So we don't want to change this kind of application scenario. We want to open new one. And so we need to consider the control part of the story, part of this system. And I think that bioinspiration can really help in having in mind an integrated design, because probably this is one of the most difficult part. Probably most of the control, because the control is part of the integrated design. But it's very difficult to understand how to design, at least in my experience. Now we really try to address the problem of the design and to consider a sort of co-evolution is too much for what I'm doing, but in the sense of co-development probably is better between the control and the body. But this is very difficult. I think from my side, this is probably one of the most important challenges that we are trying to face, because we don't have any rule. We don't have any design rule. So for the control, we are taking inspiration from the traditional robotics, but for this kind of design, we don't have any indication, any books that we can read to design our robots. And so, I mean, going through model-free approaches, machine learning applied to this kind of learning process. And again, consider the material, the body in the loop, probably, I don't know, it's not a receipt, but I don't have the solution, but it's something that we are trying to do.
I think that's a great perspective. Unfortunately, I think we're running short on time, so we won't really be able to address directly some of the audience questions here, but I want to quickly just, before we move on to closing statements, ask the rest of the panelists if they had any comments on this kind of idea of focusing on the materials and how the materials affect both the control and this idea of morphological computation, if anyone had any comments on that.
Maybe can I start?
Yeah, go ahead.
Yeah, so I exactly on the same page of Barbara, and I think really that an holistic approach that takes into account both the dynamics, physical dynamics part of the robot and the control loop at the same time. So I'm imagining something that is able to, some methods that is able to simultaneously design and choose the right parameters of the physical component of the robot and of the controller and the feed-forward action. I think that these three components have to be really designed together in order to exploit the full potential of soft robots.
Fantastic. Anyone else have any comments? Cosimo?
I just completely agree with both Barbara and Manolo.
Great. Okay, and I think with that we'll move on to our closing statements. We'll do them in the same order we had our opening statements in, but hopefully just a short closing statement so we can respect the time of our panelists, and also hopefully so our audience can stick around and hear your final thoughts on this debate. And I'd like to kind of preface this, whatever you really want to say at the end of this topic, but also what are your views on the immediate things we should be doing in this topic and the kind of further down the road future developments you hope to see in the field of control for soft robotics. So to start, Cosimo, if you'd like to say anything to close.
Yeah. Can you hear me?
Yeah, yes, I can hear you. Yes.
So a lot of things to say, but I will for the interest of time, I will just very briefly. I mean, first of all, I don't know if we will have the opportunity later, but so I will do it now. I want to thank very much all the organizers, Marwa, Hadi, Alexis, Amy, and you, Laura, for the amazing job in the moderation. I mean, I think it was a very nice discussion today, and I hope to see more and more of these things happening. Going really to the core of the question, I think that at the end we learned today that we are agreeing on much more points than we disagree. I mean, in my view, most of us is proposing to move part of the controller to the body and not to use something else. I mean, as I said before, we are talking of not using microprocessors, not very much about not using classic techniques. And I really don't see any real way of get rid of traditional methods. But on the other hand, I completely agree that with the point that Helmut and Barbara and also somehow Trish did, that all these new ways of seeing to the problem are thought. We are still using control theory, but we are doing that by pushing our view out of the box, and I think that's the very important things. And for the future I mean, I think that solving the classic problems of control theory, being precise, being able to do dynamic motions in presence of contact with the environment and doing that model-based control, I think that's something that we have to solve, even if we believe that in the long term is not the preferred way, but this really means that we really understand how this system works. And without that, I think we cannot move on. But in the long term, I really see these two words, these two views to the world to integrate each other, and control theory try to solve much more nice and crazy problems that soft robotics is presenting.
Wonderful. Helmut?
Thank you. I also would like to thank everyone who organized it, and also to thank you for leading us here. Very well done. I jotted down a couple of points. I think I would agree with Cosimo. We agree on a lot of things, and I always like this kind of discussions because it's so the goal for me is not to convince somebody that morphological computation is very important, but rather to understand my own understanding of morphological computation and how other people see it. And I always learn a lot, and so it was the same today. So thank you for talking to me about that, or let me be part of that. Now, I just want to reinstate a little bit about this out-of-the-box thinking. And I would like to give a couple of examples that I think that might be useful to understand what I mean by that. And I will use control theory terminology here. So, for example, what we have seen in our group is quite often that we see disadvantages or things that are often perceived as a disadvantage in a robot can be actually, not all the time, but sometimes can be actually be positive. And give you some examples. For example, if you look at hysteresis, which usually is something really hard to model, well, not hard to model, but it's more complex to model. You try to avoid hysteresis in a robot, in locomotion, for example. But through morphological combination, you could look at it as a way, for example, to get additional information about your movement, right? If you move back and forward, so basically you have your limit cycle, and by knowing if you up here, you know you're coming from this side. If you're down there, you know you came from this side. So you get this information by swinging a leg, right? If it's retracting or protracting, you actually get this information in the hysteresis of the system. Bifurcation, again, something that could be quite tricky, but this could be a very elegant way, for example, to switch between different behaviors, right? You have like locomotion, and then suddenly you have one parameter, and then suddenly it's a reaching movement, exponentially stable one, for example. And you get for free this kind of analog system suddenly gets binary. So you have a controller that only pushes 1 degree of freedom in one direction, and then it's stable there if it's well designed, and stable in the limit cycle as well. Under actuation, again, which is something that you don't want to have usually in control because you want to control every single degree of freedom, ideally. We've shown that this could actually serve as a computational resource, right? If you control everything but input, the system itself doesn't do any computation. It's like in a digital computer, if everything is filled by the input, there's no real computation going on. So you could see the same in under actuation. And many, many more things that you could think about, things that are negative when you look through the classical lens, but actually can potentially be positive if you use it in a proper way. Then another point I would like to say, I really liked Barbara's approach to think about different types of control for different types of soft robots. And I think the ones that we're working on, where we try to make them as autonomous as possible, they should be very robust, very adaptive. These kind of robots would need more kind of morphology, while using soft robotics, for example, for still in the factory maybe, but handling fruit, for example, right? Their more classical control theory can actually be much more useful as well. So this is kind of gray zone in between, obviously, but I think we all agree morphological combination is not the solution for every problem, nor is any classical approach. At the end, it's the same with soft robotics and conventional robotics. At the end, you want to find systems where you have the best solution for every problem here. And finally, I talked a lot about assumptions that we have, and I just want to be clear about it. I have assumptions as well. I have my own box where I'm sitting in. Some of the assumptions I'm aware of, other I'm not. So I think this deep debate or this discussion was very important, and we should have more of those. I think it's important that the next generation of new researchers coming into the field with different background, with new assumptions, right? Breaking our assumptions basically to push the field forward. I think this is something that is really important, and I think people who have organized that have done really well in doing that. Thank you.
Fantastic. Thank you, Helmut. Manolo, if you have some quick closing comments in response or just in response to the debate in total.
Okay, so thank you very much again, also from my side, to let us be here. It's been very interesting and exciting to be here. As final statement, I can just emphasize the fact that we still need, in my opinion, to take all the components together. So design of the physical dynamics, design of the dynamics that can be induced by the control, and design, so to say, planning of the fit for reduction. I think that these three components, the selection of these three components cannot be done separately. And I think that from the model point of view, even if I don't expect that at some point we will come up with precise modeling of everything, but I think that some problem we have to really carefully looking into that. And I think that a major issue is that in the field is lacking a model with some specific properties and an agreement of the community on this model be used. So an equivalent of the series elastic model. Let's say I think that this would open a lot of pathways, research pathways to solve several problems. And more than that, we have really holes in the planning and control literature for soft robots. We don't have adaptive controllers. We don't have robust controllers. So there are really holes to be filled in these years. And I think this will be decisive components, decisive contribution to have this robot at work in the world.
Great, thank you. And Trish?
Great. Once again, thank you very much, Laura, for this amazing job of coordinating this. And then thank you very much, Mawa and Hadi behind the screens did a wonderful job in organizing this and giving a lot of publicity. And yes, so, and IEEE RAS, Technical Society, Technical Committee on Soft Robotics, for taking, being very bold in opening up this debate in public. So because many things could go wrong. And then I thank the panelists, Manolo, Cosimo, and Helmut for this pleasant and nice, enlightening discussion. I learned a lot from this discussion. So what is our challenge now? I think just like, you know, consumer electronics, the smart consumer electronics, smartphones and things like that, whenever they broke that barrier of reaching massive markets, right? So everything became cheaper and much faster in the development of, you know, embedded computing and everything. It should happen to robotics, right? So the robotics should be consumer robotics, and then, but the only thing that stands on that way is something is missing in contact control, right? So we cannot trust these robots to be in contact with the child or elderly person or in a household, or, you know, handle a pet without killing it. So we have to tackle this problem, and then we are through. So I think that requires a new way of thinking, that goes beyond this separated way of thinking, an object to be controlled and a controller sitting somewhere, either numerical in a CPU or a hardware dynamic, but thinking in terms of a holistic thing, right? So everything help, like even the hamster, for example, helping, being part of the computation to solve the problem. It's a mutual thing, right? So if the hamster is relaxing, I don't have to do anything to begin with, right? So if it is relaxed, I don't have to grab it, or I don't have to grasp it. So the problem is solved. So this holistic approach requires to understand how this dynamics and computing happen in the same substrate at the same time, and then how hierarchical control systems work with local autonomy, and then some kind of centralized planning and model-based control, but without taking over everything, one taking over everything over the other, right? So everything taking responsibilities in their own sense. And then in terms of we are talking about fourth industrial revolution, right? So that requires a lot of fast, rapid iteration of products, right? So the robots, if they like even it can be a vacuum cleaner, so you should be able to rapidly iterate its designs, both the controllers and the hardware, right? So and that requires concurrent design and co-design, so that it is not just a controller and then keep your crappy hardware design, right? So you have to rethink about, and that requires a holistic thinking. So that, I think, for that, morphological computing point of view can help, and it doesn't mean that there's a separation between morphological control and control, right? It is the same. It is the same. So we are just expanding or opening it up a little bit more, and then relax these assumptions, and then make it more real world, right? So that's our challenge. I don't know how to do it, and then it's open. Basically, it is for our community to think about it.
Great, thank you, Trish. And last, to close us out, I'd like to hear from Barbara. What are your closing remarks on this debate?
So many thanks also from my side to the organizer, to you, Laura. Thank you very much for your job. Great. And so to conclude very quickly, I would like just to touch another aspect that probably will need a dedicated debate in this TC, that is the role of the materials, of course. We are talking about soft robotics, morphological computation. So again, related to the complexity of the control, we need to consider the geometry, the arrangement of the material of our robots, because this is fundamental when we want to design the robot that really interact with the environment. In nature, the arrangement of the materials, the arrangement of the muscle, the fibers play a fundamental role in reducing, again, the complexity of the control, because this is an aspect that we have to consider. Not only develop a more sophisticated control, but also try to reduce the complexity. And again, what is fundamental is start from the design. I would like to mention again this important role in our job, because if our design is wrong, then we need to put a lot of effort in the control, in the energy, again, that we need to operate in a real environment, because this is the main target that we have: real environments, complex environments. And so energy, again, is one important point that we need to consider, that is strictly related to the control, to the strategy that we want to implement. But I think that material play an important role. And so we need to understand how we can imitate from natural organisms, or in general, how we can extract the features in terms of geometry, arrangement, interaction again with the environment. So for me, bioinspiration means that, not for copy nature or having a replica of the natural organism. This is not the goal, but it's trying to understand how we can reduce the complexity, how we can save energy, how we can really act in real world. And so, again, materials are fundamental. I think that this community have to address more and more the role of the materials, the role of the geometry, how to really interact with the real environment. And I'm really happy to be part of this community, because also today, the discussion were great. I think that in our community there is not the application, not only that, and I started with that, but there is a science. There is a poor discussion. We are, discuss about how we can go forward, and we can propose a new solution, robotics for real application, for society, for user, and so on. And so, thank you really for organizing this event and for the great discussion. Thank you.
Thank you, Barbara. And so with that, I'll close out our inaugural soft robotics debate. There is a final poll, so those of you who are still sticking around, even though we've run a little late, if you'd love to vote whether you are more on the side of approaching from maybe a morphological computation or from a traditional robotics side, and we can see how this debate may have swayed people's opinions one way or the other. But either way, I'd like to thank all of our panelists, thank Barbara, Trish, Manolo, Helmut, and Cosimo for joining us today and sharing their thoughts on what I think is a very important topic of discussion in our field, and will help us push forward this next kind of batch of soft robots that will hopefully be more capable in our world and in our applications. I'd like to thank Kathy, Alexis, and Amy, and all the support of IEEE RAS for helping put on this debate today and making it so we could have all of you guys here listening and all of the panelists here.